One of the most important types of functions that we work with is called a linear function. So we're going to spend the next chapter really diving into what these linear functions are and how we can use them to model real-world events. So first, let's take a look at really defining what is a linear function. As simple as it sounds, a linear function is just a function whose graph is a line. Now that's probably oversimplifying it, and I use the word function and line in the definition. So maybe it's better to say it has a constant rate of change. And we're going to be really interested in that rate of change as we try to model various things. Linear functions always have the form of y equals mx plus b, or f of x equals mx plus b. Now that m, for both of these, the m represents that important rate of change. Or another name for it is the slope. B is going to represent what you might call the initial or starting value. Or you'll also hear it referred to as the y-intercept. And with the f of x notation, m and b mean the same things, the rate of change and the initial value. Now, a couple things to note is that the sign of m tells us the direction of the line. What I mean is if m is positive, then we are increasing. So if we're talking about an amount of money, if m is positive, we have more money over time. When m is positive, it is increasing. If m is negative, then it is decreasing. So again, using the example of money, if we have a negative value for our m, that means we have less money over time because it's decreasing. Let's scroll down a bit and take a look at an example here with a little bit more space. Let's say you get inside of a cab. In a taxi, the meter reads $3.75 when you get into the taxi. Then it adds $1.92 for each mile. Now what I can see here is my rate of change. What's changing about this taxi cab ride is the amount I pay for each mile. That's $1.92. I'm going to write dollars per mile, or we would normally put the dollar sign in front of the number, but just for the sake of the units, the rate of change is $1.92 per mile, and it's going to increase, which tells me that my slope, or my rate of change, is a positive 1.92. That's the rate of change, what's changing over time. The initial value is that $3.75. That is my b value. And so when I think about y equals mx plus b to model this situation, we can say that the cost of my ride, let's use c actually, the cost of my ride is going to be my slope of 192 times the number of miles I go plus my initial value of 3.75. And so now we have an equation to model this situation. I could even go one step further then, and now I could use this equation to estimate the cost of a 15-mile trip? Well, I'm just going to plug those 15 miles into the miles in the equation. The cost is 192 times the 15 miles plus the 375. And if I were to put that in my calculator, I'd see the cost for this trip is $32.55. Now, I mentioned with these linear functions, the most important thing to us is that rate of change. We talk about it all the time in mathematics and applications of linear functions. Often we have to calculate the rate of change because it's not going to be given to us. So when we're calculating the rate of change, the big important formula we're going to use for the slope is we take the second y-coordinate and subtract the first y-coordinate, and then divide it by the second x-coordinate, subtracting the first x-coordinate. This is an important formula to know for linear functions. So for example, if I know the point 2, 3 and 6, 1 are on my line, we can find that rate of change, or slope, because a point is always x, y, x, y. We always start with the second point and subtract the first point, although the order doesn't matter as long as you're consistent. So the second y here is 1, minus the first y is 3, over the second x is 6, minus the first x is 2. Well, 1 minus 3 is -2, 6 minus 2 is 4, and I can reduce that fraction to -1/2. I now know m, my slope, my rate of change is -1/2. Now I can look at the equation y equals mx plus b and start to build it. But you notice we're still missing the b. To get the b, we're going to use what we know. We can use either one of our points. I'm just going to use the first point. And we're going to plug what we know into the equation. Y is equal to 3. M we know is -1/2. X we know is 2. And that should help us find the b. Well, multiplying -1/2 times 2 is -1 plus b. Add 1 to both sides, and 4 is equal to b. Now I can give my equation in y equals mx plus b form. Y equals m, -1/2, x plus b, but we know b now is 4. We know the rate of change is -1/2. The starting value, the initial value, is 4. Let's kind of change the way the problem is presented to us, though, and see if we can solve a similar problem. If f of 3 turns out to be -2, and f of 8 turns out to be 1, let's see if we can find the equation for these. Well, one thing that's going to be helpful is we're used to seeing f of x equals a y. So what we can see here is this really represents the points 3, -2, and 8, 1. That's going to make it like the other problems we solved. Our slope is y2 minus y1 over x2 minus x1. The second y was 1, minus the first y is -2, over the second x is 8, minus the first x is 3. And if we're subtracting a negative, it becomes adding, so we have 3/5 for our rate of change between these 2 points. Again, we can do y equals mx plus b. Use the first point to start plugging in and figure out what that b, the y-intercept, is. The y was -2. The slope was 3/5. The x was 3 plus b. Multiplying, we have -2 equals 9/5 plus b. And in order to work with this, we're going to need a common denominator on the left. So -2 is currently over 1. I'm going to multiply top and bottom by 5. It's going to give us -10/5. That way, when I subtract 9/5 from both sides, I can see b is equal to -19/5. Now that we have our slope, our rate of change is 3/5. We have our b, our initial value of -19/15. We can say the equation is y equals 3/5 x minus, because it's negative, 19/5. Something else I can observe about this example and the example before it, because that 3/5, the slope is positive, I know this graph is increasing. Things are getting bigger because my slope is positive. In the prior example, the slope was negative. And because the slope was negative, I can see my values are decreasing over time. That slope tells us that important piece of information. All right, let's go back to applications, because like I said, with functions, we want to be modeling the real world. And linear functions are often very helpful to help us model various situations. For example, if the population of a university was 8,417 in 2005. And had grown to 9,712 by 2010. Can we make an equation to model the linear growth of this university's population? Well, one thing I notice is the population is growing, so I would expect my slope to be positive, because a positive slope would represent growth and increasing. Another thing I want to do to make this problem a little easier is, let's say we are going to start in 2005. We're going to say 2005 is the beginning of all time, because that's kind of our starting point for our information here. So we're going to let 2005 be the start year. That means our b is already known. The y-intercept, what is the value at the starting year? 8,417. The nice part about picking the start year in the right spot, because we don't have to do all that work to figure out what b is that we did in the prior two examples. Now, if 2005 is the start year, that means it's year 0. The population was 8,417. 2010 then is 5 years after the start of time. So 5 years later, the population was 9,712. And now I have my 2 points to figure out my rate of change, or the slope of the population of this university. Recalling the formula of y2 minus y1 over x2 minus x1. y2 is 9,712 minus 8,417 over 5 minus 0. Using my calculator to help me out a bit, that's going to be 1,295 over 5 minus 0 is 5. Dividing by 5 gives us 259. That means my rate of change, my slope is the rate of change, is 259 students per year. And so now we've got our starting population of 8,417. We know we've got a rate of change of 259. So if y equals mx plus b, we can say our y is equal to the slope, 259 students per year, plus the initial 8,417 students. And this now becomes an equation that we can use to estimate the number of students at another given year. This is linear growth. This is just an introduction to these linear functions. We're going to spend a couple videos taking a look at them closer, but take a look at practicing some of these and let me know if you have any questions.